This is a toy model because whether I say that the frequency equals 9 times 10 to the power of 9 as an abbreviated approximation of the frequency of the electron transitions of a cesium atom, where the actual frequency of the cesium atom is the given standard for a standard institute SI length second, or I say that frequency 9 equals 9 times 10 to the power of 14, i.e. moving into the ultraviolet range of electromagnetic radiation, the fact that I'm using an abbreviated Planck's constant means that my positive and negative exponentials are floating somewhat disproportionately. And because my laptop screen is broken, and I am doing everything on my phone screen at the moment, I haven't bothered with the multiplying and dividing of the positive and negative exponentials. Okay, so quantum mechanics holds all measurements relative to the SI length second, where time in quantum is considered to be absolute. Yet our theory of gravity, general relativity, disagrees and states time as dynamic. I am now going to show you how, by introducing a time dilation factor and changing the length of a second, I can alter the magnitude of Planck's H constant. Why would I want to do that, you might ask? Well, you shall see. First, I'm going to present consideration A, which is in keeping with my modification of general relativity, where my modification is testable and falsifiable via a clock comparison experiment. In keeping with my modification, I am introducing the axiom plus energy equals shorter seconds, i.e. faster time. Consideration A won't take very long to present, and after we will look at consideration B, which is in keeping with general relativity, where if one applies the principle of mass-energy equivalence, plus energy, according to general relativity, should equal longer seconds, i.e. slower time. Here we are looking at an SI length second. Here the frequency count is 9 peaks per SI second. Measured from this SI length second, an increase in energy increases the frequency to 10 peaks per second. But the frequency measured relative to this slightly shorter second remains at 9 peaks per shorter second. As energy is increased further, and the frequency increases as measured from this SI length second, when measured relative to seconds that get shorter with increased energy, the measurement remains at 9 peaks per shorter and shorter second. I did actually go off on an interesting tangent with these numbers, which I'll include as a footnote. So here I am calculating the energy using Planck's H constant times frequency, and by altering the length of a second and dividing by the frequency 9, which is the frequency measured from each shorter second, Planck's H constant becomes variable. So what of it, you might say? Well, this is going to potentially become useful in ascertaining a particle's position and momentum at the same time. And this is why. Wavelength equals h divided by p, where h is defined as variable to shorter or longer seconds. P equals m times v, where if the principle of mass-energy equivalence is applied, an increase in energy can be considered as an increase in mass. By keeping the velocity constant relative to increases in mass via increases in energy, P increases with the increases in energy. So back to wavelength equals h divided by p, where wavelength is now equal to an increasing magnitude of h divided by an increasing magnitude of p, the wavelength can remain constant to a shorter or longer length second as energy increases. So here is the representation of action in time, and here we have a representation of action in distance. On the basis that in a reference frame which has a shorter second than ours, the speed of light will still cover 299,792,458 meters per second, let's say these electrons, we'll look at photons later, these electrons are travelling at a constant distance at a constant velocity, where the constant velocity is held relative to each differing length of second. When this electron is here, this electron is here, this electron is here, and this electron is here. When we are here, which in time is 6/9 of an SI second, looking at this distance here, we'd have expected that at that distance, 7.5 peaks of frequency 10 would have occurred by that time, when only 7 peaks had occurred at that distance, and at 6/9 of an SI length second, the electron has already completed its 8th peak and is here. So you see, by rendering Planck's H constant as a variable in this manner, we can now know both the momentum and the position of the electron without any uncertainty. So to conclude consideration A under the axiom of plus energy equals shorter seconds, we can see that length of second is proportional to wavelength and inversely proportional to energy and frequency, where energy is proportional to frequency and frequency is inversely proportional to wavelength, when frequency and wavelength are held relative to an SI length second. And for consideration B, where we are invoking mass-energy equivalence and general relativity states that time ticks slower on the bigger mass, we are now considering that plus energy equals longer seconds, where length of second is inversely proportional to wavelength and proportional to energy and frequency, where energy is proportional to frequency and frequency is inversely proportional to wavelength, when frequency and wavelength are held relative to an SI length second. Anyway, it's clear to see that consideration B is just a simple matter of doing everything back to front. This consideration, where plus energy is equal to more mass, still applies, so in keeping our wavelength constant, I find that as an action in time, the constant length wavelengths can easily be visually represented as increasing in frequency within the longer length seconds. Interestingly, when I try and fit this arrangement into a constant distance, this starts to resemble curved space-time. But bearing in mind that measured from each longer than an SI second, the frequency will remain at 9. These electrons are travelling at a constant distance at a constant velocity, where the constant velocity is held relative to each differing length second. When this electron is here, this electron is here, this electron is here, and this electron is here. When this electron is here, which in time is equal to 1 SI second, looking at this distance here, we'd have expected that at that distance 10 peaks would have occurred by that time, when in fact only 9 peaks will occur at that distance, and this electron at time equals 1 SI length second will have just completed its 8th peak. So again, by keeping wavelength constant via increases in h and p, we can know the momentum and the position of the electron without any uncertainty. I did mention earlier that I went off on a tangent on these numbers. In asking myself how Planck would calculate his h constant in a reference frame with a faster ticking clock, I took my toy model further. As I moved Planck from the SI seconds reference frame into the reference frame of each shorter second, what became clear was, where the frequency 10 was previously frequency 11 in the reference frame of the SI length second, the magnitude of energy that Planck calculates with his increased h constant for frequency 10 is the cube of the difference between the magnitude of energy Planck calculated at frequency 11, measured with an SI second, and the magnitude of energy he calculated at frequency 10, measured with the shorter than SI second, where this difference between these magnitudes is equal to the difference between the magnitudes of the variable h constants defined for the reference frame of the SI second. The magnitude of the constant Planck defined to calculate energy in this reference frame of a shorter than SI second is the square of this difference. Where the variable h constants I defined for the shorter than SI seconds reference frame differ from those I defined for the SI second, the difference between each set of variable Planck's constants is the inverse square of the next reference frame's Planck's constant. The difference between the difference of these variable h constants sets of each reference frame is the inverse square of the greater number and the inverse cube of the next reference frame's h constant. That when a reference frame's set of variable Planck's constants are pushed into the higher energies, there is a slight fluctuation of increase and decrease in the last digit of the difference between the constants, where fluctuations are observed in temperature increases. And finally, while noting that this is a toy model, these relationships hold between each reference frame. So I asked myself, by which physical reason might Planck measure more energy at frequency 10 from a second that is shorter than an SI second than he would from frequency 11 measured from an SI length second? The answer I came up with is, it is because in a more energetic reference frame, where I am saying that Planck's clock will tick faster, the magnetic field energy of that reference frame's environment is also increased, and this increase of magnetic field strength might add to a particle's energy level when in that reference frame. Thinking further, while noting how it's clear enough that the frequency of a cesium atom's electron transitions defines the length of an SI second in our reference frame, the obvious question to ask was, which frequency of electromagnetic radiation should the SI length second be associated with? And my answer was that the SI length second should be associated with the frequency of light that is in the region of 5 times 10 to the power of 14, i.e. the visible light that sits at the peak of the Planck curve just before intensity drops off. So this arrangement here would be divided by 5. Now we can conduct a thought experiment. Planck is measuring his constant from a cesium atomic clock in an environment where his clock is ticking so fast that gamma rays are measured at 5 times 10 to the power of 14 Hertz. Consequently, Planck's constant is huge. Planck discovers that his curve peaks with gamma rays and then drops off. This opens the door on 2 questions. The first being, are there more exotic radiations at energies greater than gamma rays that are hidden from us behind a time horizon? Secondly, would the possibility of observing the lower frequencies be reduced behind a time horizon? Considerations as such that might well be of interest to anyone who is into Rindler horizon physics. So far I have been talking in terms of matter waves and photon production intensity, but let's have a quick look at photons. A photon cannot travel faster than the speed of light. The speed of light is held relative to the length of second of the reference frame it is travelling in. Light of differing frequencies all travel at same speed, as far as we know. In the case of a black body, the input energy has been transferred to electrons which produce photons at a greater frequency as energy is increased. Once the photons have been emitted, unless the emitter or receiver are in motion, or the photons change position in the gravity potential, the photons will be measured to remain at that same energy and frequency. So in the instance of a photon, there are 2 choices available. No matter if we are looking at plus energy equaling shorter or longer seconds, either I say that because of the speed of light constraint to each reference frame's length of second, I cannot say each photon of different energy in that reference frame completes a distance in differing times. So when keeping the wavelength constant via h divided by p, where h and p are increasing with increased energy, each frequency of light must then take a different path through curved space. Or, more favourably in my view, and this can be inverted for consideration B, where plus energy equals longer seconds, i.e. general relativity remit, I can say that once emitted by an electron in a reference frame, photons trade energy with the magnetic field strength of the reference frame that they are travelling in. And via the equation wavelength equals h divided by p, where h and p increase with increased energy, I can keep the wavelength constant, and in each reference frame say that photons with a frequency greater than 5 times 10 to the power of 14, as mentioned earlier, want to travel faster but require more energy trade-off than the magnetic field contains in that reference frame to retain the greater momentum, and will be reduced in velocity inversely proportional to their energy. And photons below the frequency of 5 times 10 to the power of 14 want to travel slower but are receiving more energy trade-off from the magnetic field, which increases their momentum and will be increased in velocity inversely proportional to their energy, resulting in photons of all frequencies travelling at the constant speed of light as held relative to the length of a second of any reference frame. And these increasing in energy photons all complete the distance simultaneously, i.e. the speed of light cannot exceed the local rate of time. Now, I don't know about you, but where time can be thought of as the rate at which events may occur, for me it makes much more sense that events occur faster where there is more energy. Looking at the strength of the magnetic field, reducing by the inverse cube law with increased distance from source, which inverts to the magnetic field increasing by the cube law with reduced distance to source, photons travelling towards Earth blue shift in frequency as calculated relative to an SI length second. And according to my modification of general relativity, that adds an additional time dimension and associated time dilations, this being for where m equals 0, or in other words for the places where matter isn't, and states that plus magnetic field strength equals shorter seconds, the length of a second in the magnetic field will decrease with increases in magnetic field strength as the photon approaches Earth, thus giving a physical reason for the gravitational shifting of light in both directions represented in a flat space without using the mathematical notation of g. A link to my published paper where I describe this type of flat space, how gravity can be described purely in the terms of changes in the rate of time, and how a cyclic universe can evolve as a function of these changes in rates of time, is provided in the comments. Thanks for watching.